Thank you very much for joining us. My name is Assaf. I am from PubNub. I've been there for over 2 years now. Doron is going to join me over 4 years in PubNub, and we're doing great things. The company is doing amazing things. We want to share and tell you a story about how things are going and where we're headed. You know, we have customers, and our customers have customers, and you are building things for your end users, and the demand that is coming for them is changing. They're asking for more real-time, more connectivity, more reaction from the application, and that's very important. We see that. And in the last 2, 3, 4, maybe 5 years, we've seen more and more companies asking to be able to handle stream of data, as opposed to one big video or one big file. And this is what we're going to be talking about today. So we are going to be talking about the movement. We're going to be talking about how we can address it. We're going to be talking about different architectures and how making the network much smarter actually address some of those some of the issues that we've been presented with. I'll start with a quick 30-second video. Fantastic. So the application of today, we were not able to make those same applications 3, 4, 5 years ago. The demand is different, and we're going to be covering a definition of what are those real-time applications. So everything that is social, very interactive, one-to-one. I want to tell you something. I want to signal something for you. I want to start a new movie. I want to send an event that is happening on the game. Very social related. We have companies, products in the IoT and smart homes, things like I want to open the garage door. It needs to be really fast. I want to dim the light in the house. I want to turn on the speaker. I want to be able to move data from a mouse, computer mouse, from one screen to another screen. It's all really real time, really a key that we get responsive really fast. More examples of real-time applications are connected vehicles or connected other devices, things like Lyft and Get Taxi. We need to, in real time, be able to tell where we are located, where is the taxi, which taxi is available, did I move, did the payment transaction happen correctly. Another example in the financial world, and this is more of a lot of information coming into one place. Let's call it even fan-in. We want to know stock price. We want to see a trend. We want to be able to send, for example, a signal to a phone that says, yes, you can take money out of your ATM right now because we identify that you are who you are supposed to be. So again, very important to keep it interactive. And you see a couple of our customers are using this. Online collaboration. Imagine this big object, a big design object that needs to be managed, need to be filtered, need to be moved from side to side. Many people all over the world in this specific company need to be able to collaborate in real time. I think Google Docs, etc. Imagine huge companies with a big community need to talk and ask questions. Buyer asking a seller questions and vice versa. Moving transaction from all over the world in real time. And another great example is audience participation when Coca-Cola want to notify 2, 3, 4, 5 million customers at the same time and let them know that something is happening. Imagine the other way around. Everybody in Times Square, New York, see this big screen and they want to impact whatever is on that screen, and people are voting yes or no, or 1 and 2, and those transaction needs to be all captured in one place and submitted to the big signs or whatever the company is doing with it. So very popular real-time app. We all know they exist. It's not that there is a dial tone to the internet and everything just happening automatically. We need to think how we're actually making this happen. We used to work this way. We used to have clients talking to servers, and the conversation went something like this. Do you have something for me? Nope. Do you have something for me now? Nope. Do you have something for me now? Actually, yes, I do. Here is something for you now. And then again, do you have something for me now? And this is very expensive. Lots of bandwidth, lots of battery consumption on smaller devices, and bandwidth. It is ineffective. And then, a few years ago, we moved to streaming. And look at the right side, and you'll see all devices, all sorts of devices. It can be a garage door, mobile, server, anything else, talking to each other in a different way. Whenever I have something to say, I will deliver it to the device. When the device has something to say back to me, this message is going to be sent back. And this actually presents the high-level concept behind a data stream network. This is a loosely coupled way of sending data, and work on a very simple mechanism of publish and subscribe. So you see all devices can talk to any other devices. The global data stream network just exists. It is all over the world, fit in data centers, and whenever something is sent over there, the data is just sent to the other devices. That presents a great opportunity. Now, we don't need to worry about managing scaling of system. You know, the great success of our app means we're going to coming into a bottleneck. Something will not work. Something may fail. And this is one way to look at a three-tier architecture. And we're asking, does it really work? We see all those devices communicating with the Datastream network, and then communicating to the server and asking different questions. And the data and the logic are in two different ways. It's going to be difficult, and the next slide, hopefully we'll show that to you, to actually assure quality of service. More and more devices are going to be added to the system. Your operation is going to be more and more successful, and as it grows, it's going to be more expensive to add more servers. It's going to be more complex to maintain it as you need to add more and more servers. We're going to have latency problem, reliability problem, and overall the whole experience is going to be less than ideal. Again, as we add more devices and we add more servers. So let's see. So we, after having the data stream network and after sending so many messages and helping other applications and companies to scale, we start asking different questions. Is the logic in the right place? If we need to move lots of information from one place to the other just to ask a simple question, are we doing it right? And a couple of examples. For example, chat logic. If device A is talking to device B, do we really need to send that information to the server just to see if there was any profanity? If device A is talking to device B and who talk to device C, do we really need to send all that information back into the server just to count number of messages? Does it make sense? You see, as the app is getting more and more successful, more and more devices talk to each other, the more data stream network, which is already ready to scale, is taking over, and more server need to be added to do this calculation. Another type of logic. Let's say we want to see that I have a taxi 1 mile from me. Do I really need the taxi to be able to send the information to the server to do some geofencing calculation before it's actually before we actually tell the driver, sorry, the client, the app, if the taxi is really near me. So another logic that today traditionally we are sending back to the server. Another example, alerting. Let's say we have a fire extinguisher. We have something else that sends alert all the time, and we send alerts. And every 5 seconds from every device, let's say 1 million devices, and all of them today are growing fantastically with the data stream network. But once we need to ask the question, should we alert anybody, we actually do it from the server itself, meaning that every one of the transactions are going to be sent to the to the backend server, the server will ask the question. What if we could do it a bit different and have the logic closer to where the data is? Another example, we talked about Watson before. So Watson have the ability to assess the sentiment of a conversation. So do we really need to send the information back to the server, consult with Watson API, and then answer the question, or can we put the logic more or less where it is? And last example is game logic. Do we really need to have the logic at the server just to verify different things, high score, user behavior, et cetera, et cetera? I mentioned that before. We believe that the solution is going to be to put the logic close to the data. And as you can see in the drawing, we remove the need for server for many of the simple use cases. And now we have DSN, which is Datastream Network, and the logic in one place. So with that, I'm going to be moving the mic to Doron, and we're going to be talking about this and more.
Very interesting, isn't it? So what Assaf basically presented until now is the case for a programmable network. We haven't talked about actually how it's being implemented, but it's basically talking about all the different challenges of what leads to that type of architecture. And to me, when I think about that, I don't know, to those of us that kind of encountered the era in which people introduced object-oriented computing and why use objects, there was good reason why people started coding in that metaphor. And now there's a whole class of applications that can use data streams as a metaphor. Think about it as stream-oriented computing, right? Where you have devices and applications that are streaming data to one another in real time, because there's so many classes of real-time applications across all sorts of use cases that can use that. So now we're talking about, well, some things are still the same, where if you have to put the logic somewhere, you put it in the server, and you saw, as Assaf explained, that it doesn't scale as you have more and more devices that communicate to each other, because you do the long-haul routing of those data streams all the way to the logic, which may be stuck on some back-end cloud servers. So now, start moving that logic into the network, and then we need an effective mechanism of actually making it happen. Now, keep in mind that there's probably going to be multiple different implementations of that network-centric computing going forward. It's a very big concept. I think PubNub is one company, of course, that is going to provide a solution. There's Cisco that came up with another concept. Maybe some of you saw that, which is fog computing. It also touches on that type of architecture. And it's a good thing. There's going to be multiple computing architectures that support that concept. And here what we'll present basically is the PubNub specific implementation. And I'll show you there's some other big companies such as Ericsson and Cisco that happen to actually invest in PubNub and are big supporters of that implementation, which is called PubNub Blocks. You can see it's some of the tenets of that Blocks implementation, where you're basically deploying JavaScript scripts directly into the network. They execute the logic inside the network itself. Imagine a distributed network. They're triggered in real time because if the data streams are dispatched between devices and apps in real time, you want to make sure something operates on those data streams in real time. So, and I'll talk about the type of logic and give some examples going forward as well. So those JavaScripts are supposed to automatically scale with the growth of the data streams. They are supposed to automatically deploy all the way to the edges of the network, right? You want the logic to be closer to where the data streams originate. You want to make sure that uptime is guaranteed, right? You don't want failures inside the network. You want to make sure that you have, if something needs to be updated or replaced, it can be done basically in real time as well. You want the logic and the storage to be distributed globally. I'll give some examples why you want to do that. 5.9 reliability and uptime, and of course security inside the network itself. And okay, so basically some of the principles of execution of blocks globally has to do with the fact that you want to remove latency. Some simulation here where if somebody is pushing code, it gets distributed and made available globally across the data stream network everywhere. Same thing with updating the block functionality. So if you have the previous version available, and of course the data streams continue to get deployed, the new version gets pushed, distributed to the network, so now you have a hot replica of the new code. And then what happens is that you want to deploy through the network the new functionality of the logic. Right now we have both versions available. The Datastream network deploys the new version of the logic, and what happens after that, the old version gets shut down. But the users see no interruption, so there's a smooth transition between the old version of the logic and the new version of the logic. So you have those live updates. Also, what you have here is replicated global storage, where the logic is located. You also have the logic, the storage available with it. There's an example for that. I think the font will be slightly small here, but basically, let's imagine that you're deploying an application that needs to use a shared counter, right? So every time you increment the counter, you want to make sure that the logic, wherever it is globally across the network, has access to the latest value of that counter. So you need that storage replicated everywhere in real time to be available to the distributed logic. Of course, ease of use is also very important. Tenet of the blocks, and with JavaScript, there's millions of developers that know JavaScript. We so much use run-of-the-mill, standardized JavaScript, and a lot of people are familiar with that. To deploy the logic, you have command line interface for managing the deployment lifecycle. You have very easy to use graphical user interface to get started quickly, and how to put your specific logic and compile, update it, and push it into the Datastream network. Now, with respect to what blocks are available, so you can run your own custom JavaScript code to implement blocks, and it can be anything. Using the publish-subscribe metaphor, you basically consume data streams. They're received usually as JSON messages, and then you can run your own custom logic and operate on the incoming JSON message streams, and then you can publish them to other channels, and it kind of works seamlessly and very nicely with a publish-subscribe. But many times you want to use blocks that are also implement specific functionality. So what PubNub has done is actually provide a very large number of sample blocks, and by the way, they are open source, so you can modify the code, so you can kind of learn by example as well. And they are, if you want to do bots or Internet of Things or chat and social, charting, graphing, geolocation, you have all those samples, I believe, started from about 20 examples of those blocks, and now they grew to about 60. And this was a fairly recent release, so expect hundreds and hundreds of blocks to be available going forward. Here are some of those specific examples. I welcome you, by the way, to check the PubNub website. You can see a growing list of those blocks available, all the way from simple hello world, all the way to chatbots, etc. There's also third-party partners that take more complex canned functionality, and they partner with PubNub to basically provide through blocks access to those functionalities. So not everything, basically the idea is that not everything has to be implemented inside the block itself. Sometimes what you want the block to do is to make an external API call to a third-party service, let the third-party service do its thing, and then get the result back into the block, maybe apply some additional logic on it, and then publish it. I don't know if you're familiar with some of those applications. For example, if you want to integrate email sending using SendGrid, or if you want to do some mapping functions, charting. Wolfram Alpha, for example, will give you access to very sophisticated analytical and mathematical functions. Wolfram Alpha is the makers of Mathematica, if any of you work with them. Xignite provides access to financial data streams, for example. So a lot of those are representing pretty significant intellectual property of third parties that are available to you in the form of access using JavaScript from within the blocks to access the third-party services. Some more examples here. You have, for example, detection of outliers in a graph. You can calculate all sorts of functions such as mean, median, or maximum, minimum, things like that to deploy into charting applications. Another cool example, if you have, I don't know if you know Hangman game logic, where you basically have a distributed peer-to-peer game. And typically what happens, and those players, of course, are in remote geographical locations, is that one of the players is designated as being in charge of the logic of the game. Now imagine if that node goes down, typically the game is over. You have to restart it. But if you're deploying the game logic inside a block, right? So now you have uptime, availability, reliability, security, and everything. You can't fake out the players, right? It's in the hands of the network. It's not in the hands of one of the players that can basically fake the game. And if something crashes, it can be automatically restarted by the network. So you have the reliability, and now the overall quality and scalability of the game is improved using that architecture. I think Assaf may have mentioned language translation, for example, is another common use case. Whether you use a third-party service, it can be Google or somebody else, or anybody that provides that type of functionality. IBM Watson in this example simply can be integrated into a chat. So you have two people chatting, one speaks Spanish, the other one speaks French, and they can talk back and forth to one another, what the block provides on-the-fly translation operating on the data streams that are flowing between the people that are chatting. So one other thing I wanted to show you is a little bit more elaborate example, but not too elaborate. And that's the kind of a concept app whereby you have a group chat application, can run on web, mobile clients, etc. And the people that are chatting are basically an editorial team that is trying to tweak an image. Maybe they are working on some image they want to prepare for publication, and each one of the persons chatting wants to say, I don't like this image this way, do this to the image, maybe magnify it, maybe resize it, maybe crop it, maybe change the colors, etc. So it's an example of a collaborative application where the keywords that are automatically identified in the chat stream are being used by blocks in order to dispatch those commands that are doing the editing of the image, and the image is being shown back and shared in real time among all those people that are chatting. So in that example, there's a chat management block that is responsible for parsing the chat streams and identifying the commands that are basically pronounced by or typed by the people that are chatting. And then you have another block, which is an image management block. And that image management block is talking to an image and video management service by the name of Cloudinary. Cloudinary is a scalable cloud service that provides administrative functions, so you basically functions along the lines of digital asset management, and then you can have the ability to upload images, store the images, transform them, and then deliver them, similar to the way a CDN is doing it, like an Akamai, back into the clients. And the beauty of this architecture is where the group chat is powered by the serverless Datastream network. Datastream network is passing the streams to the blocks, right? It's an integral part of how the Datastream network operates. And then the blocks are also talking to each other, right? For example, the chat management block, as it's parsing the commands out of the chat stream, basically talks to the image management block and tells it, okay, comprise, that REST API call, make that REST API call out of the commands that you identified in the chat stream, and then issue administrative commands, do transformations, and then pull it back into the clients. Again, everything here that you see is all serverless. So, the application may look something like this. And again, I'm not in a fashion industry, for example, so excuse me if this doesn't represent necessarily the way this app works, but hopefully it illustrates the concept, which has to do with So I'll give an example of how the conversation would work, right? So this is the chat screen at the top left here, and then on the right side you would see the image that is being edited, right? And those folks that are chatting are basically trying, this is a company called Acme, and they're trying to basically collaborate to choose an image and then transform it into something that would be acceptable for the fall catalog. So Joe says, hello everyone, thanks for joining the chat. We're going to review our latest collection of designer dresses and choose a few of the best pictures for our fall catalog cover. Okay, all good. So what happens here is, as you see the chat progressing, highlighted in orange here are basically the parsed keywords that the chat block is identifying in the stream. And Sarah says, let's look at the collection together here. Please, every time it says please, basically gives a signal that some command has to be identified and then put together for operating on the image, and said, please upload library fall collection pics. Since everyone's using Chrome browsers, please display images in WebP format, which happens to be the optimal format for Chrome that everybody is looking at. So now you see the image is showing up on the right. And then Dan says, looks small, please resize to 1024 pixels wide. And you see the image now is being enlarged to the right size. And then Lee says, seems flat, please auto contrast and auto sharpen. And what happens here? Kind of looks sharper, isn't it? Better contrast, right? So the image management block is doing its thing, basically operating on the image as the people are chatting, and those commands are parsed and put together. And then Joe says, looks like the dress is off center. Please set gravity to auto, pad crop mode with black and crop. I don't see our logo. It needs to be there. Do you agree? And now it's centered. And Sarah says, please overlay Acme 30 by 60 pixels logo at southwest corner, and then the logo shows up. Okay, good. So basically, everything that you have seen implemented using a serverless configuration, using a Datastream network, and two blocks, that chat management block and the image management block. Okay, so to sum it up here, basically this serverless architecture is agile, where you don't have to worry at all about DevOps. It's kind of included in the whole development and deployment lifecycle. It's just click code and deploy. And then I mentioned earlier that Cisco and Ericsson are in support of that architecture, and over 900 companies are signed up for early access to blocks. So if you're interested, you can go in there and sign up. It takes about 2 minutes and get instant access to that concept and start coding away, especially if you like JavaScript. Makes it very easy. And that's it. I'll just leave you with some of the stats of the extent of the deployment of the Datastream network now, including blocks as well. Thank you.